So today we are going to be starting with a bunch of MCQs from the topic of chemical equilibria. So let's get started. Okay, so we're going to do recent past papers. This is May-June 2024 in paper 12. So let's get going. Nitrogen dioxide reacts with water. Okay, so we have nitrogen dioxide, we have water, we're forming this nitric acid and this nitric acid. They're not nitric acid, one is nitrous acid and the second one is nitric acid. So one is nitrous acid, this one is nitrous acid and this one is nitric acid. But at your level, you don't need to know the names. Just consider them as two different acids, okay? Which statement about this reaction is correct? Okay, so now let's see what kind of thing is happening. We have a oxide, we have a non-metallic oxide, which is nitrogen dioxide, and we are reacting it with water to form two types of acids. So what's unique about this reaction is that we're forming nitrogen in two different types. Okay? So now let's read the options. Both products are formed because oxygen atoms gain electrons. Oxygen atoms gain electrons. Don't you think that's not happening? You don't have any oxygen atoms in this reaction. You have oxide ions. There's a difference between oxygen atoms and oxide ions. When you have oxygen in water, you don't have any oxygen atoms. Oxygen atoms mean 8 electrons in total, whereas oxide ion means 10 electrons in total. So there's a difference between oxygen atoms and ions. Oxygen atoms last shell is going to look something like 1, 2, 3, 4, 5, 6. This is oxygen's atom last shell. Whereas for an oxide ion, the last shell is going to be something like 6 electrons are going to be thrown, 1, 2, 3, 4, 5, 6, and 2 are going to be gained from another atom. So this one's an oxide ion. And what's happening is there is oxide ion in this nitrogen dioxide, there are oxide ions in this water. There are no oxygen atoms that are gaining electron. Oxide ions remain oxide ions in HNO2 and HNO3. No change of oxidation number for oxygen in this reaction. No oxygen atoms involved in this reaction, only oxide ions involved. I hope that makes sense and this concept is clarified. Nitrogen atoms undergo disproportionation. Okay. So now we need to check the oxidation number of nitrogen changes or not. Let's see. Now the thing is we have to check the oxidation number. For first, we have to check the oxidation number of nitrogen in nitrogen dioxide, and that's going to be a positive 4. Why? Because look, one oxygen is going to be undoubtedly a negative 2, because oxygen is always negative 2 unless it is bonded with fluorine. Then it's going to be a positive thing. Otherwise, oxygen is always negative. Or in hydrogen peroxide, oxygen is going to be a negative 1. But otherwise, in all chemistry, oxygen is going to be a negative 2. Acha. Now, oxygen is a negative 2 and there are two oxygens. So, negative 2 multiplied by 2, that makes it negative 4. You have a negative 4, and to balance it out, you need a positive 4. So, one nitrogen is going to have a positive 4. So, now let's check for the oxidation number in HNO2. Okay, so over here, oxygen's oxidation number is going to be a negative 2. And since we have two oxygens, the oxidation number is going to be, for two oxygens, going to be negative 2 multiplied by 2, which makes it negative 4 for oxygen. Okay, for oxygen, it's negative 4 total. For one oxygen, it's negative 2. Up to balance out negative 4, you need how much? You need obviously you need a positive 4. Positive 1 is going to be given by the hydrogen, because hydrogen can either get positive 1 or negative 1. So a positive 1 is going to be given by hydrogen. So what's left? A positive 3. That's going to be given by your nitrogen. So nitrogen is a positive 3 in HNO2. And in HNO3, since there's a 3 here, that means oxygen's negative 2 multiplied by 3, that's going to make it a negative 6. Oxygen in total gives a negative 6. Okay? 3 oxygens in total. Hydrogen is going to give a positive 1. How much is left? Positive 5. To balance out in negative 6, you need a positive 6. Positive 1 is already there. How much more do you need? You just need a positive 5. So nitrogen is going to be a positive 5 here. A positive 5 here, a positive 3 here, and from a positive 4, it's going into a positive 3 and a positive 5. That's indeed disproportionation reaction, whatever. So that is disproportionation reaction, because a single kind of species is both undergoing reduction and oxidation. There's a decrease in oxidation state going from +4 to +3. That's a decrease in oxidation state. And then there is oxidation as well, going from a +4 to a +5. That's an increase in oxidation state, which is going to make option number B the correct option. Okay, the oxidation number of hydrogen is increased. No, it's not. Hydrogen is a positive 1 in water, and hydrogen is a positive 1 here and here as well. So not at all. You might think there's a 2 here. A 2 means that positive 1 on one hydrogen, a positive 1 on other hydrogen. So in total you have a positive 2, but on a single hydrogen it's going to be a positive 1. Okay? Water acts as an oxidizing agent. Okay, if water acts as an oxidizing agent, it has to be reduced itself, right? It has to be reduced itself. But the oxidation state of hydrogen over here is a +1. For oxygen, it's a -2, right? For oxygen, it's -2. +1 and this -2, they need to be reduced, because in oxidizing agent, what happens is that it makes the other substance lose electrons, and it itself gains electrons, and itself is reduced. But over here, look what's happening. This positive 1 remains as positive 1, and remains as positive 1 in nitric acid as well, and in nitrous acid as well. And this -2 remains -2 in this and this. Okay? You don't have to look at the total oxidation number of two oxygens. You have to look for one hydrogen, for one oxygen. For two hydrogen oxygens, it's -4, but for one, it's going to be -2. So it's not undergoing reduction or at all. So it cannot be an oxidizing agent for sure. Moving on to the next reaction, it's about KCKP thing, an alcohol ROH. It's from a latest past paper, May June 2024, paper 11. Reacts reversibly with ethanoic acid to produce an ester. Okay, so you have an alcohol. This is an alcohol. It's reacting with an acid. This is the ester that we're going to have, and this is water that's produced. And what kind of substance catalyzes this reaction? You should know it. Sulfuric acid catalyzes esterification. Okay, we're not concerned with the catalyzation over here. We're concerned with the KCKP values. 3 mole of ROH, 2 mole of ethanoic acid, and 1 mole of water mixed together. Okay, so now we're given with the initial moles. Okay, so now let's draw the perfect table that you should always draw whenever you have to find a Kc expression or a Kp expression. No matter what you have to find, you always have to draw this table. Okay, so we write the reaction and then we draw the table. So the reaction is going to be that we have ROH, which is an alcohol. We're making it react with ethanoic acid. Okay, and then we are producing this ethanoate. This is an ester, and we're producing water. Now we're going to first write the initial moles for all of them. This table is very important, like a very, very, very important thing. So you need to write the initial moles of all the things that are present. Okay, the initial moles of this ROH alcohol are 3 moles, 3.0. Okay? 2 moles of ethanoic acid, 2.0 moles of ethanoic acid, and 1 mole of water. And you have 1 mole of your water mixed together. This means in the beginning, you have 0 moles of the ester. You have 0 moles of the ester because it's not given in the question, then we're going to consider it 0. Okay, at equilibrium, 1.5 mole of your ester is present. Okay, so now the second part is going to be about used moles, which we don't know right now. And the third part of this beautiful table is going to be about the moles that are going to be at the equilibrium. So the third part is going to be equilibrium moles. We have 1.5 moles of this ester. Yeah? Look at the beauty of this table, that it's going to make you solve every question easily, like in seconds and minutes, once you're proficient with it. You don't have to draw these lines every time. You don't have to decorate it. You don't have to do anything. You just have to plug in the values. Okay? Acha, up now, you need to use some ratio thing. Okay? You can see one thing from the equation clearly. Okay? Every equation, equations are beautiful things. You know why? Why are they so nice? Because they tell you the ratio in which the substances are reacting together. Equations are the best things on earth, because in chemistry, they're gonna tell you how much ratio of things are reacting together. Okay? For 1 mole of this thing, how many moles of that thing you need to make a substance? So now, over here, the ratio is 1:1:1:1:1. So that means K, if 1 mole of this is used and 1 mole of this is used, we are gonna form 1 mole of our ester and 1 mole of water. Okay? If 1 mole of this substance and 1 mole of this substance, they're gonna be utilized, we're gonna be forming 1 mole of an ester and 1 mole of water. So if 1.5 moles of this ester are formed, that means that 1.5 moles of our alcohol and 1.5 moles of our acid are going to be utilized, because look, the ratio is 1:1:1, and we know that 1.5 moles of water are going to be formed and 1.5 moles of our ester are going to be utilized, of our acid and alcohol are going to be utilized, because the ratio tells this. Okay? So that's the beauty of ratios. So 1.5 moles of this utilized, 1.5 moles of this utilized, 1.5 mole of this formed. Now, okay, now since 1.5 moles of this are used, you also need to keep in mind one more thing. That what's happening is, initially you wrote 1.5 here, okay? But listen to me. That's not correct. I just wrote it for you guys to first understand the thing. I told you 1.5 moles of water are formed. Okay, you might say yes, 1.5 moles of water formed. But look, 1.5 are formed and 1 you had initially. ठीक है? अब यहाँ पे initially 0 थे और 1.5 फॉर्म हुए, क्योंकि यहाँ पे 1.5 फॉर्म हुए, हमें पता है यहाँ पे 1.5 फॉर्म होंगे. अब यहाँ पे 1.5 फॉर्म हुए वाटर के मोल्स. ठीक है? अब यहाँ पे क्योंकि 1.5 फॉर्म हुए हैं, सो वी नो वन थिंग, दैट इनिशियली हमारे पास 1 तो पहले ही थे. सो प्लस 1 mole, and that's going to be 2.5 moles of water. You get it? So we produced 1.5 moles and 1 we had initially. So they're going to be 1.5 moles of this, 2.5 moles of this at equilibrium. And the third thing, now we have to figure out the products. These are the products. The products are formed. Okay? They're formed at equilibrium. We saw 1.5 moles of this being formed. We saw 1.5 moles of this being formed. But what happens with the reactants? They get used up. So for reactants, what do? We subtract. From 3, we are going to subtract 1.5 moles because 1.5 moles are used up. So 3 minus 1.5 is going to give me a 1.5. 2 minus 1.5 is going to give me a 0.5. So these are my equilibrium moles, and that's all I need. 1.5 moles of this alcohol are going to be there, 0.5 moles of my acid are going to be there, 1.5 moles of my ester is going to be formed, and 2.5 moles of my water are going to be present. Now I have the moles of everything at equilibrium. The next thing I need is the concentration of all these things. For concentration, I need the volume. But I'm going to tell you one very beautiful thing about Kc expressions or Kp expressions. When you have equal number of moles on the product side and on the reactant side, you don't need the volume. You know why you don't need the volume? Because in a Kc expression, the volume is going to cancel out eventually. Okay? the volume's gonna cancel out. So even if you don't take the volume, because 1 mole of this, 1 mole of this, total 2 moles on the product reactant side, and 2 moles, 1 mole of this, 1 mole of this on the product side. So they're gonna cancel out. So no worries for the volume. So even if you take the volume as x is going to cancel out, because Kc at the end has going to have no expression. Why? Because equal number of moles on both sides. Whenever the equal number of moles on the reactant and product side, Kc has no units and you don't need the volume. Just write this down somewhere. This is a very important line, that whenever you have equal moles So now, since we know our Kc expression is going to cancel, so we don't need the volume. So now let's put in the moles of the reactants above in the Kc expression, that are going to be 1.5 multiplied by 2.5 and divided by the moles of the product of the reactants. The products are going to be at the top. Okay? Products are going to be at the top. The reactants are going to be below. Okay? Reactants are 1.5 and 0.5. Plug this value in your calculator. Let's see, what do we get? We are doing 1.5 into 0.5 into 2.5, and I get 5 as my Kc constant. So it's going to be 5, which is going to be option number D. Okay? Okay, graphs can be drawn to show the percentage of ammonia at equilibrium when nitrogen and hydrogen gases are mixed at different temperatures and pressure. Which diagram correctly represents these two graphs? Okay, so now when we mix nitrogen and hydrogen, okay, at different temperatures and pressures, the percentage of ammonia that's formed is being described on the graph. Okay, which diagram correctly represents these two graphs? So first, let's write down the equation that we use for this thing. We have NH3 that's going to be produced. You know, that's a reversible reaction. So NH3 is going to be produced something like this from our very own nitrogen and hydrogen. You have 3 moles of hydrogen, you have 1 mole of nitrogen, and you form 2 moles of your ammonia. Okay? So now let's see what's happening. Okay, so now first we need to realize one thing, the effect of temperature and pressure. This is an exothermic reaction. Okay? So exothermic reaction. That means that if we increase the temperature, ammonia should decrease. Okay? If we increase the temperature, ammonia should decrease. Okay? Firstly, we know one thing, that at equilibrium, if we increase the temperature, ammonia should decrease. So let's write out, since it's exothermic, so if we increase the temperature, ammonia should decrease. Why? Because in exothermic reactions, when you increase the temperature, equilibrium move backwards. Okay, the second thing, we have a total of 4 moles here and a total of 2 moles here. So if we increase the pressure, we have pressure, if we increase it, equilibrium will favor the side with less moles, because you know that equilibrium always favors the side when increasing pressure that is less moles, and when you decrease the pressure, equilibrium move towards the side that has more moles. Increasing the pressure will increase NH3 at equilibrium. Okay, so first thing we know that what's going to happen is that if we increase the temperature, ammonia should decrease. So for a higher temperature, less ammonia should be formed. This one. Okay, for a higher temperature, less ammonia should be formed. So this one. Next is pressure. Okay, what should happen? Okay, what's basically is happening is that when we are increasing the pressure, ammonia is decreasing. So simply, देखो, if we increase the pressure, our ammonia thing should also increase. So over here, look, we are increasing the pressure from 0, it's going to 10, and then it's going to 20. We're increasing the pressure, but what's happening is that ammonia is coming down by increasing the pressure. That's wrong. When we increase the pressure, our ammonia should go up, not come down. So it's gonna be for sure option number D, that our ammonia is going up as we increase the pressure. Why? Because less moles on the product side. So increasing pressure would mean that equilibrium shift towards the product side. I hope you get this. Okay. Now we have that's a redox question. Okay, which reactions has an equilibrium constant that has no units? I told you any reaction that has equal number of moles on the reactant and product side is going to have no units. So for option number A, there are 2 moles on the reactant side, 2 moles on the product side, 1 mole here, 1 mole here. So option number A. Let's solve for other parts as well. For option number B, there are 3 plus 1, 4 moles on the reactant side, 2 moles on the product side. So no. Okay, for option number C, it's 2 moles on the reactant side, 1 mole on the product side. No. Equal moles on reactant and product side cancel out the Kp Kc expressions. So what you're looking for, equal moles. The key concept in this MCQ is equal moles. 2 moles here, 1 mole here, 2 mole here. No, a total of 3 on this side and 2 on this side. That's not bearable. Okay.